difference is going to be small. So now let's solve an example that basically make us understand how all those three equations are useful. What three equations? The phi equation, the omega equation, and the enthalpy, right? So he has a duct, and this air is coming in, and he's heating the air. So that is typical of the HVAC application. We will get air from the outside, and we don't like this air. The people over here waiting for that air, they don't like it. Either it's too cold because we are bringing it from the outside, or it's too dry, or because it's winter, or it's too humid because it's summer, or it's too hot. The point is, we will not like that air, and we will do something to this air before we send it into our room or into the factory, right? And so what usually you do, the easiest thing is to add heat or subtract heat. Okay, adding heat is much easier, because you will see when we take out heat, that could actually cause the water to condense, right? We'll see this later. But anyway, adding heat, that's the easiest thing ever. So let's add heat so that those people don't get too cold. 10 degrees C, that's too cold. They want it to be at 30 degrees C. Okay? And so what he will ask for us, he will ask about the output, or he would say, if I want to have this, how much Q? Okay? So he could either give this and ask for this, or give this and say, guess what will happen here, right? So in this scenario, 10 degree, 80% relative humidity, phi is 80%, and this is the flow rate, right? And he's asking, in order to have T2 30 degrees C, how much is the heat transfer? And look what unit he wants for the Q dot. He wants it per kilojoule. It's in kilojoule per kilogram of dry air. And you know why? Because the way we calculate the H is per kilogram of dry air. So he's really just trying to make our life easier. When we do the first law, everything will just be per kilogram of dry air rather than per kilogram of mixture. Okay? So the first thing he's asking for omega 2. Right? The humidity ratio at the output. So let me ask you, what equation are really going to control this problem? Remember, we have only three equations in thermofluid. We have continuity, momentum, and energy equation. So when he asks about how much heat does it take to take the air from 10 to 30, what should we, which equation should we use? Energy equation, right? Because it has the Q dot. However, yes, energy equation, that's correct. But we will always, we always use actually the continuity equation. The continuity equation will always be useful for us. And that also the case in fluid mechanics. If you remember, in every scenario, whenever they ask you for calculating the force and you say, yes, I would use the momentum equation, most of the time you also need the continuity equation to start with. Because m dot is always there. In the momentum equation, there is m dot out v out minus m dot n v in. In the energy equation, there's also q dot minus w dot equal to m dot h out minus h in. So the m dot is always there, and so the continuity equation is a given. You have to use it. And also when you say, well, give me the humidity ratio, what is that? Kilogram per kilogram, right? Kilogram of water vapor per kilogram of dry air. So if he's asking for kilogram, we need the continuity equation. And even if he didn't ask for W2, you know that when you apply the energy equation, you would need m dot, right? So you will have to use you have to use continuity equation. All right. So let's think about part one first. So by the way, the pressure is constant. He said that the mixture remain at constant pressure, 1 bar. So 1 bar, 1 bar, right? 1 bar is 10 to power 5 Pascal. Okay, so this is heat addition at constant pressure. Very good. So W omega 2, the humidity ratio at the end. So I bet I can get this, how many kilogram of water vapor at the end? I bet I can get it from how many kilogram at the beginning. Why is that? Because he's just adding heat. So if you're adding heat and you have like few water molecules over here, so a certain kilogram of water vapor is coming per unit kilogram of dry air. Will they change at the exit? They will not. And how did I do this? Did I guess that? No, I just apply the continuity equation. So actually we have two continuity equations in this problem. One for the water vapor and one for the dry air, because they are two different species, right? So we can actually apply the continuity equation for each one of them, the mass, because they don't really change species, right? The water vapor will not become dry air, and the dry air will not become water vapor. They are completely two different species with completely two different masses, right? So here is the continuity equation for the dry air. He's simply m dot air 1 equal m dot air 2. Steady state, right? M dot vapor 1 equal m dot vapor 2, right? So will this always be the case in all the problem? Well, the air will, right? Unless you are taking air somehow out. But most of the time, m dot air in equal m dot air out. Now, the m dot water in equal m dot water out, that will not always be the case. When will it be different? If the water is planning to condense, leave the vapor state and drop as water droplet that we will collect from the floor in a drain, right? So that happens a lot in air conditioning. You know, have you ever been in a city where they have those windows units out of the windows, and then you walk in the street and it's all dripping because of the, or actually in your car, have you ever been like in the summer and you watch there is this water under your car and it's coming from the condensation of the water, right? So if we cool the water too much, it could drop, and m dot water 1 will not be equal m dot water 2. Fortunately, this is heating, and in heating, no, the water will remain the same, right? So this is the case. And so, all right, so then he's saying, what is this m dot vapor? That is m dot air, dry air 1 multiplied by omega 1. And how much is m dot vapor 2? How much m dot vapor leaving? That would be m dot air 2 times omega 2, right? And so since m dot air 1 equal m dot air 2 equal m dot air, right? Then what is left here will be the omega 1 equal omega 2, right? So omega 1 equal omega 2. So since he's asking about omega 2, maybe I have better luck getting it at 1 and then say 2 equal 1. Why can I get it at 1? Because I got my phi. Remember, if we know phi, then we know p vapor, and if we know p vapor, we have this equation, the one that say what, 0.622 p vapor over p air minus p vapor, the omega equation basically. So that's what we will do then, right? So you say you got your phi 1 0.8, you can get BG1. How did you get BG1? 10 degree C. Open the steam table, find out what's B saturation and 10 degree C. It should be 0.01228 bar. And B vapor 1 will be 80% of this. We got it. And here is the omega equation, 0.622 B vapor over B mixture minus P vapor. What's P vapor? What we just calculate from here, right? And you got yourself the 0.622. That was the constant. Remember the mixture molecular weight, the dry air molecular weight, and the water vapor molecular weight, and we divided and stuff. Anyway, so we got this, this, and here's the one from, he said it's 1 bar. Here is omega 1, which is omega 2. Done. Done with the first part. The second part is heat transfer. How much does it take to take you from this condition to this condition? First law of thermodynamics. Q minus W, which I don't see any W. There is no compressor or pump or anything here. Q equal m dot, the way I memorize it is q dot equal m dot 2h2 all 2, huh? Minus m dot 1 h1, the whole one state. Okay, and if we add q, that's plus. If we take q, that is negative, right? So here it is, q minus w equal, and again I memorize it, you put it on the other side. On the other side it is m dot out h out minus m dot in h in. Okay, I think it would be nicer if you just remember it always in that form. But anyway, this is exactly the same. So if in case you wanna just bring this formula from the book, that is fine with me too. But I really think it should be written like this: q dot minus w dot equal m dot 2 h2 minus m dot 1 h1. So what is m dot 2 h2? You got two things at the exit, right? You got m dot dry air multiplied by h air, which it's dry air 2 plus m dot vapor, and we said there is no m dot vapor 1 and 2, they are just m dot vapor because he didn't change the mass of the water vapor. H vapor 2, that is 2. And this is the case for the inlet. 1 m dot dry air 1 h air 1 plus m dot vapor h vapor 1. He's pulling m dot air together, and he's saying h air 2 minus h air, and then he's bringing m dot vapor together, and he's pulling those two guys over here. That's fine. And then here is the part when he divide over m dot dry air. So he divide over m dot air dry air, he get 1. He divide over m dot dry air, he get omega, fortunately for us. And he divide the q dot over m dot dry air. And so now if this, we calculate this, that would be joule per kilogram of dry air, not joule per kilogram of the mixture. Okay, so to get this we need those guys. So the air is leaving at 30 and he came at 10, and omega, we just calculate omega, we just need those two numbers, right? So the air CB delta T, or you can just actually use the table, it will be more accurate. Why it will be more accurate? Because the CB delta T, what's wrong with CB delta T? Anyone? What is wrong with CB delta T? What's wrong is you're assuming CB is constant, and CB is function of temperature. So if you can bring it from a table, this will be more accurate, because the table will count, will take into consideration the CP part. Okay, very good. We got the omega, we just calculated this 0.006, and remember I told you the omega is really tiny, right? We said it's 0.00 of order of 0.001. Here we go, so it's really small. All right, and now this is the part that if we have steam table, go for it, get it accurately. With what? You need pressure and you need temperature, and you'll be able to do it, right? And what pressure? The vapor pressure. And so at the beginning we know the vapor pressure, right? Why we know? Because we know phi. Now at the exit, do we know the vapor pressure? And you would think, well, shouldn't it be the same? Well, the partial pressure is the same, right? So the vapor pressure would be the same. But here, rather than going for the vapor pressure and going the temperature and calculating from the steam table what's the enthalpy at 30 degree and that vapor pressure, he is saying, let me just approximate this to Hg. So he's gonna go for H saturation at 10 degree and 30 degree. All right, and yes, you are now probably are not feeling comfortable and like, why? But this actually, those numbers he's getting over here multiplied by this tiny number will end up basically saying 0.22. So that delta H for the dry air is 20, and the delta H of the water vapor, because it's multiplied by a very tiny omega, 0.006, it ends up 0.22. So whether you end up using the correct H vapor or you approximated it to the Hg, which is the saturation enthalpy at those temperature, regardless of the fact that, well, I'm not B saturation, I'm actually lower, right? Because my humidity was not 100%, my humidity was 80%, and we will know shortly that when we even heat the air, the humidity ratio will drop and drop and drop, right? But anyway, you can see that the difference wouldn't change that much. It would be rather than 20.32, it would be what, 20.35, 37, right? So you know what's 0.05 between friends. So the book will use this approximation.